So today we're going to cover section 4. We're going to talk about perimeter and area in the coordinate plane, as well as classifying polygons. So the first thing though we need to do is define what a polygon is. So the word polygon, if you break it apart into say suffixes and prefixes, the word poly means many. And then the word gon, the last part of it, means angles. So the word polygon means many angles. Now, a polygon is a closed plane figure that's formed by coplanar segments called sides. Now, each side must intersect exactly two sides, one at each endpoint. So for example, if I make a side or a segment, it then has to intersect the other two sides at exactly one endpoint. The smallest polygon that I can create is a triangle because again, it has to be a closed figure. No two sides with a common endpoint could be collinear. So for example, I couldn't draw and put some collinear points and say that this is the side of my triangle. Again, it can only have 2 points and make a segment. You can't have 3 different points all on the same side. And then each endpoint of a side is called the vertex. So I have vertices right here where the two sides meet. So A, B, and C would be my vertices of that triangle. So what we're going to do first is identify some pictures, and you have to tell me if you think they're polygons or not, based off of this definition and then these 3 characteristics of it. So the first one, figure A. Is that figure a polygon? And this figure is a polygon. It's closed. Notice the sides. They're just single segments. We do not have collinear points. And each of the endpoints is a vertice. So yes, this is a polygon. However, as soon as I removed and made a hole in it, and it's not a closed figure, figure B is not a polygon because of this hole right here. It's not a closed figure. Figure C, this star-looking thing, this one is also not a polygon because notice I've got 3 points here. I cannot have collinear points that are forming a side. And it's also, these points are intersecting too many sides. So this is not a polygon. The next one, as soon as I took away those inside lines here, this is a polygon. It's a closed figure. Each one of the segments is only touching the other side. I don't have any collinear points. So this one is a polygon. Yes. And then the last one, this one is not a polygon. It's not a closed figure, and the sides are not intersecting at both endpoints. So this one is not a polygon. Another thing for a polygon is notice the sides must all be segments. So if you have a figure that's got a curved side, this is not a polygon. So a polygon cannot have it can't have any, so no curved sides, or you could also think of them as rounded edges. So as soon as it curves, it's not a polygon. They have to be segments that make up the sides of your polygon. Next, we're going to classify polygons, and we're going to give them 2 names. they're either going to be convex polygons or concave polygons. Now, just to give you a little heads up, the way that I know the difference is if I see a side that looks like it's caving in, like this star, see how that side looks like it's caving in? This would be a concave polygon because it looks like one of the sides is caving in. But I'm also going to show you another way that you can determine that once we see the official definition of concave. First, let's talk convex. So a convex polygon happens when no line that contains a side of the polygon contains a point in the interior of the polygon. And what this means is, let's say I highlight this inside, so everything in here is the inside of the polygon, inside these walls. So if I were to go along the sides, so this segment here, and just extend it and make this a straight line, notice my straight line never goes into the yellow. So I would test out all of my sides. Soon as I would find a side that would go inside or into the interior, then it would not be convex. So all of these sides, if I trace over them, notice none of them go into the yellow. None of the red goes into the yellow. So this is an example of a convex. Same thing for the middle one, and I can do the same thing for here. So if I were to shade in all this interior in yellow, I would make sure that when I extended that line, it didn't enter the yellow part, and it doesn't. Now we're going to see what I mean by having that line go inside it, and you'll see that when it's a concave polygon, which is the next slide. So when you have a concave polygon, it's going to have a line that contains a side of the polygon that contains a point in the interior of the polygon. So again, if I shade this all in yellow here, this is the inside. So if I were to extend, and I don't have to have all of them go in there, as soon as I find one side that goes in there, then I know it's going to be concave. So, and again, I would look for the side that looks like it's caving in. See how this side looks like it's caving in? So that should be a clue that if I extend one of these sides and draw a line, you see how the red just went into the yellow? This would make this polygon concave. Every single side doesn't need to do that. Because notice these other ones, if I do this one over here and extend it, notice how it doesn't go into the yellow. Same thing here. So I think the easiest way to determine if something's concave is look for a side that's going inward. Same thing here. This side looks like it's going in, but they also did that line check and it went into the yellow. And again, all you need is one side to do that. Everybody good on the definition of concave? Now we're going to look at a bunch of polygons. First we're going to name them, and then we'll look at some more examples. So the next slide has all of the names for polygons that you're going to need to memorize based on the number of sides that you count in the polygon. Now, there are other names, but these are the only names that you're going to be responsible for. So again, the smallest polygon you can create to create a closed figure is a triangle, a three-sided figure. The next one, the four-sided figure, this name that's right here, quadrilateral, this is just the general name for a four-sided shape. Later on in another chapter, we're going to talk about specific quadrilaterals. In other words, squares, rectangles, rhombuses, trapezoids. So for right now, anytime you see a figure with four sides, you're going to call it a quadrilateral. Then the next one, 5 sides is called a pentagon. 6 sides is called a hexagon. Now, there are 2 words here that begin with the letter H. So to help me remember which one goes with which, I sort of think of the hexagon. It's got the 6 sides. In the word hexagon is the letter X, and same thing here with the word 6. So I know a hexagon is 6 sides. It has an X just like the word 6. And then the other H word is for the 7-sided figure. The 8-sided figure is an octagon. I think of that, I associate it, I think of an octopus, has 8 arms. So the octagon has 8 sides. The nonagon has 9 sides. This one's kind of challenging for some students. They may not have heard of this before. So if you think about spelling the word 9, notice nonagon has 2 N's here, and so does the word 9. They just switched up the vowel that's there. Nonagon has an O, 9 has an I. So a nonagon is the 9-sided figure. The 10-sided figure is called a decagon. I think of a decade as 10 years, so same prefixes, so decagon is 10. Now notice they jump over 11. You're not going to be required to memorize the name for an 11-sided figure, but you do need to know that a 12-sided figure is called a dodecagon. Now, any other shapes, and we will see some of these, that are not any of the names listed here, the way that you would describe them, for example, the 11-sided figure, so 11 sides, is called, you would just take the number of sides it has, put a dash, and then put the letters G-O-N. If you had 100 sides, then you would write 100, the dash, and then G-O-N. So the only ones you need to memorize here are the ones that are listed. Anything else, it'll just be a number, and then the letters G-O-N. Next, let's identify. Again, practice identifying if something's a polygon. And then we're also going to identify if it's concave or convex. So the next one, part A. Is this a polygon? And notice it's a closed figure. However, it's 2 closed figures together. So this one would not be a polygon. However, if I drew it like this and didn't put the line through the middle, this would actually be a polygon, and it would be convex. Because again, notice if I drew a red line over one of the sides, see how it goes in to the yellow, the interior. Or again, think about this side, looks like it's sort of caving in. So this one would be yes, and it would be concave. The next one, again, notice this one, all of the sides stop at and meet only one other side. No collinear points, it's a closed figure. So this one would be yes, it's a polygon. Now let's extend those sides. See how this one stays out? Let me go ahead and shade in yellow here. If I extended this one, so far nothing's going in. This one, nothing goes in. Here, here, here. So nothing enters that yellow interior section. So this one would be convex. Now this next one, I know it's kind of hard to see, but this is supposed to be a curved side here. And remember, a polygon cannot have a curved side. Couldn't have an arc to it, so this one would not be a polygon. And then our last figure, and if it's not a polygon, we do not classify it as concave or convex. The next one, it's a closed figure. Notice there's only a single 2 points on each segment, and they're meeting the other segment to close it. So this one is yes, it's a polygon. And then notice if I were to extend this side here, it would immediately go inside this yellow interior portion. So this one would be concave. And again, it looks like one of these sides is like pointing inward, caving out. The next slide, in addition to identifying if it's concave or convex, now we're going to give it the name based on the number of sides it has. So let's try. the next one. So for this one, I'm going to count how many sides it has. All three of these, A, B, and C, are polygons. But let's go ahead and count how many sides it has. It has 1, 2, 3, 4, 5, 6 sides. So this name would be a hexagon. And notice it doesn't look like any sides are caving in. Even if I go ahead and double check it with the lines, no lines go to the interior. So this would be a convex hexagon. Now, one other thing that you're going to see coming up is whenever you see that all sides have the same congruency marks, so you notice how this side has a single dash, same here, 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 and then all angles have the same marking. Whenever all sides are congruent and all angles are congruent, you're going to learn coming up that they could also put the word regular in front of the polygon name, and that tells you all angles are congruent in it and all sides. That'll be coming up though. So, but whenever you see the word regular, if it's a regular triangle, a regular pentagon, know that it just means all sides are congruent and all angles. The next one, we're going to count those sides. And we have 1, 2, 3, 4. The four-sided figure is called the quadrilateral. Now, later on, more specifically, we're going to learn that this is a parallelogram. But again, for now, know that it is just a quadrilateral. Then, if I take the sides and see if they go into the interior, this side does not, neither does this, or this, or this. And again, nothing looks like it's caving in, so this would be a convex polygon. And then the last one, let's count up all those sides, see what name we're going to give part C. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. And the 12-sided figure from that chart is called a dodecagon. And again, we can check to see if it's concave or convex. And we can see if we go ahead and extend one of the sides. Doesn't matter if all of them, all it needs is one. As soon as I extend this side, it goes into the interior, making this concave. And again, it sort of looks like this side right here is caving in. So the next thing we're going to do is we're still going to be graphing ordered pairs. And we're going to be able to find the perimeter of a triangle, a rectangle, or a square by counting either the squares on our coordinate plane or using the distance formula or using that other formula where we just subtract one of the coordinates when it's horizontal or vertical. So when we want to find the perimeter of a triangle, notice here the formula is just adding up all three sides, A plus B plus C. The formula for area of a triangle is 1/2 base times height. Or you might have also memorized it back in your pre-algebra days as base times height divided by 2. Either one works. Then the middle one is a picture of a square. And again, that little S is just showing that that's the side. Remember that in a square, all sides are the same, so I could label all of these as S. So the shorter way to find the perimeter, we just take the side length and times it by 4, because you have 4 of the same things. You could also just add up all those S's, and that would also give you the perimeter of a square. The formula for area of a square is side to the second power, which really means side times side. If you want to also think of it as base times height or length times width, you can do that as well. Just know when it's a square, your base, your height, your length, width, that'll just be the same number. And then for the rectangle, same formula for area. A lot of times in 5th grade, they teach it to you as length times width. And then when you get to middle school, then they introduce base times height. They both work. Now the formula for perimeter there, just remember when it's a rectangle, these opposite sides are going to be the same. So I could also, instead of using 2 times the length plus 2 times the width, I could also just add them, just like I did for the square, add them up individually. That works as well. A lot of times, probably in your Algebra 1 class, when they gave you word problems about rectangles, that was probably the equation you used. Because then you could create a 2-step algebraic equation. Now, whenever you calculate a perimeter of any shape, usually it's always going to be measured in linear units. So for perimeter, let me do it not in highlight. So perimeter, the units are always going to be linear. And what I mean by that is they'll probably say the side is in inches or feet. These are all linear units. Could be meters, could be centimeters, could be yards. So perimeter, it's going to be a linear unit. If it's just on the coordinate plane, each one of those squares is going to represent 1 unit. And whenever you give your answer, it's always whatever the unit is. But when we talk area, these linear units are going to be squared. So for example, you would write your answer for an area question as either inches squared, or you might see it written as square inches, or you might even see inches raised to the 2nd power. So it may be inches, it may be feet, whatever's labeled in the picture as the units. So let's go ahead and try an example. Now, these 2 next examples we're going to do, they're on the coordinate plane. So when I go to label my answers, I'm just going to use the word unit. So let's try example 3. Everybody good here? All right. First thing we're going to do is we're going to graph the order pairs. So I'm going to graph order pair A. It's the order pair -2, +3. And then order pair B, +3, -3. And then order pair C, -2, -3 is right here. I can connect the points to make my triangle. And now the question asked me to find the perimeter. So remember, for perimeter, we need to add up all of the sides. Now, if you recall from the beginning, whenever your line is horizontal or vertical, you can just count the squares. But when your segment is diagonal, we need to use the distance formula. So I'm going to show you both ways for the horizontal and the vertical by counting the little boxes and by also subtracting the order pairs, just like we did in the other lessons. So let's do segment. So really what we're doing here to find this perimeter is I need to add AC plus side BC, this one here, plus side AB. So this one, I must do it in black. This one over here. So plus AB is going to give me the whole perimeter. So let's work with AC first. So the order pair for A is, and we'll do it in red, -2, +3, and then C is -2, -3. So it's this red line over here. So I'm going to count the squares and do it that way. That's the fastest way. And you can only do it if it's a vertical line like this one. 1, 2, 3, 4, 5, 6. This segment has a length of 6. I can do the same thing for BC, that blue one. 1, 2, 3, 4, 5. However, for that gray one, I have to do the distance formula. Now, let's say you didn't have a graph and you want to just subtract the ordered pairs. You can get the length of AC the same by subtracting. So when you look at your ordered pairs, if you see either the x's are the same number or the y's, then that's the one you're going to get rid of. And then now I'm going to subtract the bigger number minus the smaller. So 3 minus negative 3 gives me 3 plus 3, which gives me 6. Now, if you did the smaller number minus the bigger, just remember we have to absolute value it. So if you've got a graph, honestly, it's faster to count the little squares. However, you could still subtract ordered pairs and get the length of that segment the same way. Now let's do BC. I already counted the squares. So once I do the subtraction of the ordered pairs, it should still give me 5. So let's do BC. And the ordered pair for B, I'll rewrite them here so they're right next to me. B is that one, and C is negative 2, negative 3. Again, look to see, because it's a horizontal line, one of either the x's are going to be the same or the y's, and in this case the y's are. And now I could do big minus small, so 3 minus negative 2. If you want to put the absolute value around it, do that. 3 minus negative 2 is really 3 plus 2, and then that gives me 5. So again, same answer I got. When I counted the little squares, I can get them by subtracting as well. Now, even though these are horizontal and vertical, you can use the whole distance formula. Just remember, when you do y2 minus y1, you're going to get 0. So really, you don't have to do the whole formula. Now, for AB, we need to do the whole distance formula because I can't count the little squares. So just to remind you what the distance formula is, x2 minus x1 squared plus y2 minus y1 squared, all under the square root. So let's go ahead and get our ordered pair A and B. So again, A is negative 2, 3, and B is 3, negative 3. Notice if you just quick look at them, notice both of the x's are different and so are the y's. So again, let's give labels. So this one will be my ordered pair number 1. This will be ordered pair number 2. And now I plug these ordered pairs into the formula. So once I do that, I get 3 minus negative 2 squared plus negative 3 minus 3 squared. This is all under a square root. 3 plus 2 is what this one becomes, so 5 squared. And this becomes negative 6, so negative 6 squared. 5 squared is 25. 6 squared is 36. So the length of AB is going to be the square root of 61. I can't simplify that. That's prime, so I would leave it. So now, remember, so now I could label it up here because I already put labels on the other ones. So now remember, what I told you we had to do from the very beginning was take all those sides and add them up. So AC is 6, BC is 5, and AB is square root 61. Now, when you go to add square roots, if the other numbers do not have the same square root, you can't combine them. The only thing I can combine here is the 6 plus 5. That would give me 11, and I leave the square root of 61 alone. So the perimeter of this triangle is going to be 11 plus square root of 61 units. and you would leave it apart. Now, if this were a PSAT question or an SAT where it lets you use a calculator, then what you would do on your calculator is figure out what the square root of 61 is and round it to the tenths place. It's 7.8. And then I could add that to the 11, and the perimeter rounded to the tenths place is 8.8 units. So 18.8, sorry, 18.8 units. So keep in mind, if it lets you use a calculator, you're going to evaluate that square root. But we will not, so we would leave it as a square root. Yes. Yes. Everybody good on this one? Next, we're going to do an area. Graph 3 order pairs, find the length of the base and the height, and then plug it into the area formula. So let's try example 4. So for this one, I'm going to graph order pair D. It's the order pair 1, 3. Then I'm going to graph the order pair for E. It's going to be 4, negative 3. And then lastly, F, it's negative 4, negative 3. I'm going to connect them, turn it into a triangle. And now I can find the area. So again, just to review, the area formula, 1/2 base times height, or base times height divide by 2. So obviously we need to find the length of the base and the length of the height. So the base of my triangle is this segment down here, FE. So I can go ahead and, because it's a horizontal line, I can count the little squares. I'm also going to show you how we can subtract, but let's count it first, see what we're dealing with. So 1, 2, 3, 4, 5, 6, 7, 8. So FE, the length of that segment is 8, which is our base. Now again, I could take the order pairs. F is negative 4, negative 3, and E was 4, negative 3. Notice the negative 3's, the y's are the same, so when you subtract them, it becomes a 0. So then here all I have to do is the big number minus the small, keep flip change it, 4 plus 4, and again the length is 8, which is the same answer I got when I counted the little squares. All right, so we found the base. Now we have to find the height. Now, the height of any polygon that we're going to find the area of must always be next to a right angle. Notice this is not a right triangle. So to find the height, what I'm going to do is take that highest point D, and I'm going to draw my line straight down, because you're going to learn coming up that whenever you have a line that is perpendicular, know that a vertical line and a horizontal line where they meet is always going to form a right angle. So the height I could draw in there, and now I could just count the squares. So the height of my triangle is going to be 1, 2, 3, 4, 5, 6 units tall. So the height is 6. If you want to figure out what the coordinate was when you drew down, you could also subtract those. But again, if you've got a coordinate plane and you've graphed the order pairs correctly, it's so much easier just to count whenever the line is horizontal or vertical. So now that I have both the base and the height, now I can plug it into my formula. So again, area equals 1/2 base times height. So if I plug that in, my base was 8, my height is 6, and now I'll multiply that straight across. Half of 8 is 4 times 6 gives me 24, and units on area questions are going to be squared. So you can either write it like that, you could write it as square units, either way. Now, again, what I like to do, instead of writing my area formula like that, again, I like to do I like to just do base times height, divide by 2. So I would plug in the 8, the 6, and divide by 2. You can choose to divide only one of them by 2 and then multiply what remains. And you still get the same answer that way. So either way, just take half of one of the numbers and then times it by the other. So this is how we can do perimeter and area questions when your polygon is put into a coordinate plane. We'll use either the distance formula to find the lengths of the sides, or if their lines are horizontal or vertical, just count the units. Yes?
If we're given like no graph on the quiz or the test and they're asking us to find the area, how do we find the height? Like we're just using
You're going to have to graph it because you're going to need to find the other coordinate if you wanted to do the subtraction.
Okay.
Does that make sense?
Yeah.
Okay. All right, so that is it for 1-4. You have your homework that is due on Monday. And then when you come in, remember you need to do that warm-up.